All right. Thanks everyone for coming. I'm very, very excited for today's colloquium speaker. Professor Bryan Shuman is visiting us from the University of Wyoming. Bryan is a full professor at the University of Wyoming, and I learned he plays a pivotal role in many service departments, including the promotion and tenure service committee there at the University of Wyoming. Bryan got his PhD at Brown in 2001, and then he was a recipient of the NOAA Global Change postdoc. It's a very prestigious postdoc, and he went to work with Pat Bartland in the University of Oregon. After that, Bryan became an assistant professor at the University of Minnesota. And after getting tenure there, decided that he craves the mountains too much, and he wanted to move out west. So he decided to move to the University of Wyoming. Bryan is also the director for the Center of Quaternary Studies at the University of Wyoming. And he's involved in all kinds of very cool research, and he's a pivotal member of the community there. So Bryan, he's tough to describe. He does so many various different things. He's arguably one of the foremost experts of Holocene and Pleistocene hydroclimate change in North America, period, I would say. And he's worked on vastly different things, from pollen reconstructions to lacustrine sedimentology to biomarkers to microbes. So he's really got a diverse array of tools at his disposal. And Bryan, he's got a fairly large group as well. He's got 2 postdocs, several students. Right now, I think you have 4 or 5 students, and they're all doing various diverse things. And it's really incredible to see how his research kind of takes all these pieces from different fields and puts them together in context of sort of the bigger picture of paleoclimate in North America. A little tidbit that Bryan and I are kind of weird, like you're a weird academic step uncle of mine, where my academic grandfather was this person named R.K. Matthews at Brown University. That was my PhD advisor's advisor. R.K. Matthews was a seminal paleoceanographer, paleoclimatologist. He was also an extremely curmudgeon-y guy. I've never met him, but I recently learned that he kind of adopted Bryan as an informal mentee, and we had a lot of fun chatting about RCAM and the history and so on. But Bryan, he comes from kind of a school where he learned directly from the people who were involved in things like CLIMAP and COMAP, John Embry, Tom Webb, his PhD advisor. And in my opinion, he's carrying the torch in his own different way, and really doing some interesting stuff about regional and also global changes as we go back in time through the Holocene. So without further ado, Bryan, come on up, and please join me in giving a round of applause to welcome Bryan.
Thank you so much, and thank you for that generous introduction. It's my real pleasure to get to be here to visit with you today. This is such a fantastic department. It's been wonderful, all the conversations I've had today, and get to see the facilities here. Plus, this is like 50 degrees warmer than at home, and there's no snow on the ground. I am really interested in a wide range of different topics, but one of the bread and butters for me is thinking about how our water supply has and can change. And I've been really interested in looking at this from the standpoint of the Holocene and the end of the Pleistocene, looking at how lakes in particular have fluctuated through time and how they provide a geological record then of water availability. And so a lot of what I'm going to talk about today is based on records from little lakes like this, which is up in the Bighorn Mountains in northern Wyoming. But I'd like to start off with this slide in particular, because this site is actually, we chose it because it's really closely located to one of the oldest Paleo-Indian sites in Wyoming. And it's just a great reminder that this story that I'm going to tell you about changing water supply was part of the lives of people who really owned this land and curated it and were the stewards of it for many millennia. And I just appreciate that, recognizing that history. So, oops, oh, one of them, go. Okay, so in general, my research is I'm interested in kind of warm climates because that's where we're headed. But I'm intrigued by the idea that our climates vary on sort of century to millennial timescales, and that's a timescale that we don't understand particularly well. It's longer than our direct historical observations. It's longer than even things like tree rings can easily capture, but it's also shorter than the timescale over which the geological record really can tap into. And so this has been a focus of mine. The reason I focus on the Holocene is because it's this time period that we can study quite well, and often with the resolution to look at those scales of fluctuations. And I'm interested in how water, but also ecosystems respond to those climate changes. And I'm not going to talk very much today about our paleoecological work, but we're doing a lot of work on things like wildfire history, abrupt changes in ecosystem composition, things like that, I do find really fascinating. But all of this work for me has always involved kind of a combination of field-based work that ranges from sedimentology to geophysics, and using some organic geochemistry, but then also large data syntheses to really look at climate at the scale of many large-scale climate processes. And so I'll try to give you a flavor for some of both of those things in the talk today. And of course, none of this is my own work in isolation. A lot of it is the product of these really fantastic students I've had the opportunity to work with over the years. I'm going to highlight a few of my recent graduates' work today. Meredith Parish and David Liefert have done some work that I'll show you, as well as Tessa Ray Cousin, who is part of my current group of students, which has been really fun to work on, even though we've had to be virtual so much for the last 2 years. And finally, of course, the cores that we collected that I'm going to show you some data from are actually collected, a bunch of them were collected by a team of undergraduates who were part of a program with me a few years ago. And all of this has been supported by NSF, which I'm very thankful for. So let me set the stage here by talking about water, of course, is vital to us. And I like this diagram, which you may have seen, which just highlights how if you took all the water in the oceans, it might make a single droplet about the diameter being equal to the north-south width of the United States. And if you made a droplet that was just all the fresh water, it might be the size of a small eastern state. And actually the surface freshwater that's available to us is an even smaller droplet, roughly the size of the city of Atlanta. And if you think about how little that is, it doesn't take much to really influence the availability or distribution of that water across the surface of the planet. And so maybe the total amount of fresh water available to us hasn't necessarily changed dramatically through time, but how that little droplet is spread out around the globe has changed and has profound consequences for us when it does change. And so this is something it's really useful that the geological record can tell us about, really give us a better concept for thinking about how dynamic that water supply is. So we know there's hydrologic change on lots of different timescales. A good example is the wonderful tree ring record developed here, looking at droughts along the Colorado River over the last 1,000 years. And we know that there were not only single year droughts, but droughts that lasted decades. But we also know on much longer timescales, we have the glacial, interglacial cycles. And those have dramatically altered the water supply. But the gap in here is sort of in between those timescales, is trying to understand how do things change on sort of century to millennial timescales, and that's what I've really focused on. But the geological record really makes it clear, regardless of timescale, that our water supplies can change pretty dramatically in the face of climate change. And I just like to use this picture of Death Valley to highlight that point. Here is the driest part of the country, one of the driest parts of the world today, and it has shorelines up on the hillsides there, representing the time in the past when it was a very deep lake. So if we had been people dependent on that lake, it was something that really fundamentally changed and impacted the societies that were there. And it raises the issue that, of course, our future, the resources we depend on could change equally dramatically in the future. So this talk is going to take two perspectives to look at the Holocene and how our water supply in North America has changed. First, I'm going to show you some stratigraphic evidence to look at how water levels have fluctuated in different lakes. And this is just an example. This is a ground penetrating radar profile from a lake. Here's the water up at the top. This is all the lake sediment. And then these bright reflectors are paleo shorelines that ring the lake basically as bathtub rings that preserve a record of the transgressions and regressions of this small water body. And we can study that to get to work out that history. At the same time, we use fossil pollen data to actually also look at the ecological response to temperature and precipitation change. And it can provide a sort of slightly different angle on this same problem of how has our water supply changed during the Holocene. And so I'm going to focus on two particular aspects. First, I want to talk to you about the history of the Rocky Mountain snowpack, which is so vital to us here in the West. That is our primary freshwater water supply. And then I'm going to take a look at some of the data we've been generating in the East and look at the possibility that you can have droughts that last for many centuries to even millennia, and look at the evidence for that. Okay, so let's start with the Rocky Mountain snow. I think about the Rocky Mountains as people have called it the natural water towers of the West. These are these high elevation cold areas that accumulate snow all winter, and then in the spring that snow melts and runs off, and it comes from my home state in Wyoming, comes all the way down the Colorado River, and some of it eventually makes its way to various communities across Arizona, as well as many other states. So the history of this water supply is actually really important to understand the sensitivity that it could face in the future. And this has really been driven home to me recently because I was involved in a big effort that we've done recently called the Greater Yellowstone Climate Assessment. And the goal of this climate assessment was to look at the Yellowstone region and provide kind of a baseline set of documents for people in that region to understand how it may change in the future, how it has been changing, and how it may change in the future. And the real takeaway message from looking at all the different climate variables that are undergoing change right now is that the snowpack is really significant, it faces a serious risk. And so this is a map showing kind of centered on Yellowstone National Park right here in the center, and the region around it. Here's the Wind River Range, is sort of down in the lower right-hand corner if you're familiar with that. But the map, if you focus on the blue, is the extent of the region that today receives a permanent amount of snow in the winter. Like it begins snowing now, and it'll accumulate snow all the way through till May, and then melt off and run down the rivers. But as temperatures rise over the next few decades, that snowpack essentially vanishes. And so even within a few decades, by the 2060s, 2080s, even under scenarios where we do a fair amount of work to mitigate our carbon emissions, there's a substantial reduction in that snowpack. And that if you allow the emissions to grow even greater, or you look further out in time, it basically disappears. And so this is a pretty stark lesson warning to us that this vital water supply could change and disappear with lots of consequences. So this has motivated me to want to understand what's the history of that snowpack. And the Holocene provides an interesting opportunity because there are some time periods in the Holocene that were modestly warmer than right now. And I mean, maybe actually not necessarily warmer than now, but recent decades, we're maybe already exceeding the Holocene. But it stayed warm for millennia, and there's a chance to see how much did that added warmth affect this critical water supply. So just for context, these are some reconstructions we did using fossil pollen data from all over North America and Europe. So this kind of represents a kind of land northern hemisphere perspective on Holocene temperatures 12,000 years ago to present. This is the lower graph here is the mean temperature of the coldest month. And the upper graph is the mean temperature of the warmest month. And if you look at both those graphs, you can see things were cool at the as things warmed up after the Pleistocene. But they did both in terms of summer and winter actually receive some periods of time that were modestly warm compared to the 20th century. And so that raises the question, how much did our snowpack change in response to that modest warming? So to look at this, we've been focused on southern Wyoming and northern Colorado. And I'm just focusing on a map here of Colorado to highlight the blue in this map again is where most of the snow falls. And so the mountain ranges in northern Colorado here are where we have done most of our work. It happens that this western mountain range up in the north there is probably the snowiest portion of Colorado. If you're a skier and you know Steamboat Springs, Colorado, that's where that's located. And it's located there because it has some of the largest amounts of snow anywhere in the Colorado Rockies. And the Yampa River, which drains that, is one of the major tributaries to the Colorado River. So the work I'm going to show you sort of focuses on that region and just over the line here in Wyoming. And the place to start is the work by my student Meredith Parish. This was a master's project that she had done. She's now a graduate student, a PhD student at Bryan, working with Jim Russell on other paleoclimate problems. But she was interested in this question of how our snowpack has changed. And what she did was take a number of pollen records from the northern Colorado spanning the last 2,000 years or so, 2,500 years. And they were collected from lakes that are located in areas where the forest composition is really intricately connected with the amount of snow that's on the landscape. So if you look at this air photo here, you can see these forests, these bands of forests intermixed with snow drifts. This is a very snow-dominated ecosystem. So potentially quite sensitive to the change in the amount of snow. By using the pollen as a basis for reconstruction, by taking fossil samples and matching them to modern samples associated with known ecosystems with known amounts of snow, she could make estimates of how the snowpack potentially changed through time. And what she found here was that almost all of the, basically all of the sites that she worked on across a range of different elevations all showed a several hundred millimeter increase in the amount of winter precipitation over the last 2,000 years. And down here at the bottom is just the average of those together. And there's potentially some additional fluctuations added on top of that, but clearly overall there was, based on this data set, a trend towards now being a relatively snowy time compared to the previous millennium. And this raises the possibility that even though we think of the West as very arid today, that it may actually be quite wet, geologically speaking, compared to other time periods. And that it wouldn't necessarily take very much to move it into a state where that snowpack is substantially reduced. So with this in mind, we undertook a few additional projects. And I'll highlight a couple of things, work done by a recent PhD student, David Liefert. David wanted to look at this from the physical stratigraphic evidence of how the snowpack may have changed. And what he targeted were these small ponds that were located all across high elevation areas that are essentially pools of snowmelt. And so he studied a whole range of different sites. I'll get back to the numbers there. But these are a whole set of small ponds located at high elevations, almost all above 10,000 feet in the snowy range, aptly named for this project, in southern Wyoming. And David first did some work to evaluate what controls the amount of water in these ponds. And what he found was that all these small ponds in the spring after the snow melts are quite full. And over the course of the summer, they lose up to 90% of their volume. It disappears. And so you can see these photos from the spring to the late summer, these lakes shrink dramatically. we put out a series of evaporation pans, did geophysical measurements to understand where that water go. You know, if it evaporated away, I mean, it would be totally lost from the system. On the other hand, what we found was actually that there's some evaporative loss, but almost all of this is just drainage into the subsurface. And so what's going on is you melt so much water from the snow in the spring that it floods the system and it can't drain fast enough. But over the course of summer, you just don't have enough water in the form of rain to make up for that lost water percolating in the ground. And so in a way, these become then a really great record of when you have a lot of snow melt on the landscape. And so what he did was take sediment cores from a dozen or so of these lakes and figure out, when did they first form? When did they first start becoming persistent enough to accumulate sediment? And the radiocarbon ages of the basal sediments in those cores tell a story of this landscape becoming snowier over the course of the Holocene. So this is last 11,000 years. This histogram is just showing the number of lakes that were accumulating sediment through time. Basically, each tick mark here is the basal age of a different core, a different lake. And so while a few of the lakes persisted through the whole Holocene, most of them only began to accumulate sediment sometime in the mid to late Holocene. And the largest number of them really only formed in the last 1,000 years or so, when the pollen would suggest that things are actually quite snowy. So these two lines of evidence seem to agree pretty well that we are living in a relatively snowy time period at these high elevation sites. So if you're familiar with like the Colorado River Compact and how water was allocated to the states in the West based on a very particularly wet time period, the 1920s, and how problematic that is now, put that in the context of realizing that that is probably in the wettest millennium in terms of snow of the whole Holocene, at least in this portion of the Rockies. And so the risk to our water supply from snow, from changing snowpack seems significant. But let's take one more perspective on this, and that is, up near these same lakes there are a number of permanent snowfields. And so here's the lakes, the dots of the different lakes that David cored. You can see the distribution of radiocarbon ages on there. There's no real geographic pattern to them. But the headwalls of the mountains right here have these permanent snowfields. And so we had the question of, what's the history of those snowfields? Can that also tell us something about this? And so David focused on this lake in particular, which we call the Lagoon, which is located right below one of the biggest snowfields. And the nice thing about Lagoon Lake is that it only exists really because water is running off all summer from the melting of this permanent snowfield. And as that water runs off towards the lake, it picks up lots of sediment here. You can see, like, here's the stream channel coming into the pond. It carries a fair amount of sediment from these unvegetated areas adjacent to the snowfield. And so we thought we might be able to get a sedimentary record of runoff or erosion associated with the persistence of this snowfield. And the sediment core was really striking. So this is from the center of that small pond. This is about a 3-meter long sediment core. Vertically, here's depth. And this graph over here on the left is the amount of organic matter in the core as a percent of the core material. And when you see there's actually three distinct units in this core. There's an uppermost unit that has very little organic matter, a lower unit that has quite a lot, and then below that actually another short interval with very little organic matter. These are the radiocarbon ages versus 14,000 years ago to present here. The radiocarbon chronology constraining that. And the important point is the rate of accumulation, the relationship of depth to time, was relatively slow up until about 3,000 years ago. And then it's been very rapid since then. So this is a very rapidly accumulating inorganic layer on top of a more slowly accumulating organic rich unit. And you can also see, if you just look at the density of the sediment, that upper sediment is this really dense mineral matter, whereas the lower organic rich unit is not very dense. And if you take this data set together and calculate how did the flux of organic matter into the lake change through time, or the flux of mineral matter change through time, what we find is there's not really a significant change in the organic flux. This high concentration of organic matter early on is not because that was more productive time period. If anything, the organic matter production has actually slightly gone upward. But what happened in the upper part of the core is it's diluted by a huge increase, an order of magnitude increase in the amount of mineral matter washing into the lake. So our interpretation here is that before about 3,000 years ago, there probably was not really a significant snowfield feeding into this lake. But sometime in the last 3,000 years, or right around 3,000 years ago, that snowfield became a permanent feature of this landscape and began eroding quite a bit of sediment into the pond. So if we look at that in time, here's that same sediment flux data plotted versus time, 11,000 years ago to present. We see this increase in the sediment flux. It happens to coincide in time with things becoming much cooler. So this is a pollen for temperature history. And basically when the regional temperatures were high in the early Holocene, there was not evidence for a permanent snowfield. And this agrees generally pretty well with the timing of the formation of these small ponds across the landscape. So taken together, all this data seems to support the notion that this warmer portion of the early to mid Holocene really was the time period with substantially less snow on the landscape, and raises the possibility that our snowpack is potentially quite temperature sensitive. There's more work to be done to really understand what's controlling this. Maybe it's not strictly a temperature effect directly, but there is clearly a possibility that the snowpack of the Rockies could change in dramatic ways. And unfortunately, that really underscores the message of this set of maps, this projection of the future, is that there really is a pretty substantial risk that we lose the snow from our high elevation mountains, even at some of the highest parts of the Rocky Mountains, which is a pretty shocking change if we really undergo that transition. Okay, so that's kind of a perspective on the West, because snow is so vital out here. But I want to shift gears and look at the humid East. And because the humid East is a place that we tend to talk much less about water. The East Coast of the United States, looks, there's a picture of a lake out in Massachusetts, lush forest, lots of water out there. We don't tend to think too much about climate constraining the water supply there. But it turns out the stratigraphic record of lakes there raises the possibility that even that region has been prone to some pretty dramatic changes in water supply. And you can think about this as cutting two ways. Either it means there's a risk of big droughts in the future, or it raises the fact that things can get wetter than they've been at certain times in the past. And so maybe the East is a place that might be prone to becoming flooded. But I want to emphasize a question of multi-century drought or millennial scale drought. We think of drought as being a year or maybe a decade, maybe even a string of decades during mega droughts. But the stratigraphic record, I'm not going to go into too much detail of this one, but if you look at this ground penetrating radar profile from this lake, here's the water, and there's a series of reflectors here that extend out from shore that seem to be paleo shorelines representing times when this water level has fluctuated. And so I've been curious to understand what's the pattern of those droughts and what processes might govern them. And I think I will provide the caveat here from Henry David Thoreau, which I think is really great. He wrote in the book Walden, "The pond rises and falls, but whether regularly or not, and within what period, nobody knows, though as usual, many pretend to know." So I will try my best to tell you what I pretend to know about this. Words of wisdom. So my approach here is to try to be as systematic as possible in looking at the stratigraphies of many small lakes. And this involves first surveying lakes with ground penetrating radar or seismic reflection to look at the stratigraphy of the whole basin, and then taking sediment cores from different water depths to really capture that stratigraphy in cores so we can do analyses of the grain size, organic content, but also things like the radiocarbon date, the key transitions. And that's the benefit of working in the Holocene is that we actually can do this at a lot of different lakes, and we have relatively decent age control compared to other times in the geological past. And so we can get a pretty rich history of how these lakes have fluctuated using this approach. It works because many small lakes and ponds are very simple sedimentary systems. They basically have two sedimentary facies. And you can see it in this air photo. Out in the deeper portion of the lake, it's just organic matter and very fine sediments. It's accumulating with very little energy to move that material around. And it gets down below the cool water. It's not very oxygenated, so that organic matter and the fine sediments are preserved there very well. Near shore, even a little bit of wave energy in these basins can actually erode away, winnow away all those fine materials, but also leads to the deposition of a sandy zone. And so you're kind of a near shore sandy environment versus a deep water, deep water being only a few meters deep often, of organic rich muds. And often the boundary between those two environments is very sharp. And so what I've done using GPR and sediment cores is really track this boundary through time in these lakes as a way to gauge where was the shoreline, what was the elevation of the shoreline in the past. And the stratigraphy is often quite dynamic. It shows evidence of times where that muddy zone has expanded during when the lakes are wet, and times when it's contracted and the sand has moved out into the middle of the lake at times when the lake is low. And so here's just an example of digging into the shoreline of one of these lakes, and you see the alternating layers of mud and sand representing time periods of high versus low water in the past. If we take ground penetrating radar, we can actually survey the lake, and we can actually track these sand layers as they extend out from shore out into the deeper sediments. And if you look carefully at this, you'll see that some of the reflectors out here in the mud, the deep mud section, come up and get truncated at unconformities here, which are erosion surfaces that form during these low water periods. So then by taking sediment cores through this, we can find these different sandy intervals and radiocarbon date them to figure out when the lake was at those different levels, and use the elevation of the sand to constrain the water level history through time. So here, plotted versus time over the last 12,000 years is the amount of sand in these two cores here. And you can see there's 1, 2, 3, 4, 5 peaks in sand content that line up with these reflectors that we see in the radar.
Bryan, what are you doing?
We're dating actually sedimentary charcoal and macrofossils that are sort of bracket these layers to find out when they, yeah, good question. And so what I've done is develop a really simple little algorithm to classify every sediment sample in each core in terms of being in shallow water environment or a deep water environment. And then because we know the elevation of the different cores and their ages based on those radiocarbon dates, we can plot each core, its evolution through time in terms of its elevation, and assign each sample as to whether it's a shallow water sample or a deep water sample. And then based on the uncertainties in that assignment and the difference in which facies show up in which cores, we can kind of stratigraphically constrain where the shoreline must have been through time. And so this allows us to create a time series, a quantitative time series that we can then compare across sites. That's really grounded in the sedimentary data from multiple cores. And we tried to test this method in various ways. We've cored multiple lakes in the same region and compared those stratigraphies to each other, and they tend to agree really well. And one other analysis we've done is to take the water level history of the lake, and this is the same lake I just had in a previous slide. Over the last 10,000 years, its water level history is plotted here in gray, or the black line. And I've actually run it through a simple hydrologic model to estimate how much did precipitation have to have changed to drive the volumetric change that we see in the lake level. But then in green, what I plotted out here is the pollen-based reconstruction of precipitation for the same site. So here we took pollen data, we matched all the fossil samples to modern samples, and based on the ones that were most similar, we assigned the fossil samples an appropriate estimate of what the past precipitation should have been. And what we found is that both of these systems seem to agree pretty well. They both show, and this is really significant if you think about it. Over the last 10,000 years, this is from Massachusetts, effective precipitation in Massachusetts has increased by 400 millimeters. That's the difference between being on the edge of the Great Plains today and being in Massachusetts today. So you almost, it was dry enough here, you could have plausibly had the prairie extend almost all the way to the East Coast. And both the pollen and the stratigraphy agree in the magnitude of that long Holocene trend. But they also agree in these sort of multi-century fluctuations that are superimposed on top of that. And if you plot the two data sets together in a scatter plot, there is no significant difference. The differences that are there are all within the uncertainties of the reconstructions. But I wasn't totally satisfied just with this. We tried to take it one step further. We actually took that pollen inferred precipitation, ran it backwards through the hydrologic model to predict how the water level of lakes should have changed. And then for each site, each core location, we ran it through a really simple sedimentary model to predict how much sand should there have been in each core. And so the orange here is the actual observed mineral content of the core. And the black is what's predicted from that pollen-based climate reconstruction through that set of steps. And it's not perfect by any means, but you'll see a lot of the main features of the cores are reasonably well predicted. So we have a pretty good prediction here of the observed versus predicted. It seems to do reasonably well. So it suggests that there really is a causal linkage here between what the pollen is detecting and what we're seeing in the sediments. So that's the approach I've been trying to take, but I don't care about just a single site. I want to know kind of for the whole continent, how's this played out? So we've been slowly building a network of lakes from the East Coast out towards the mid-continent and then up and down the Rockies, and using that same approach in all these different sites. And I'll just kind of give you a broad picture of the continental trends here by taking the data that we've generated and combining it with similar data that we mined out of the literature to provide some maps of how the continent's moisture availability has changed since the last glacial period. And so here's a map of North America 20,000 years ago. The gray is showing the extent of the ice sheets. And the dots are all the sites that were both ours plus other ones that we found in the literature where there was some evidence of lake level change, including the big pluvial lakes in the desert Southwest. And this gridded map, for each grid cell, we had at least one data point. And if it's blue, it's marked as being higher than its long-term average water level. If it's orange, it's marked as being lower than that average water level. And I'll show as an animation so you can just see how this pattern has changed over time. But in the glacial world is very different than today. The desert Southwest was receiving a lot more moisture. But what you see as I play out the animation is that, of course, the deserts here will dry out, but so will almost the whole continent. The whole continent in the mid-early Holocene becomes exceptionally dry. And then, not that it becomes a desert everywhere, but it's just drier than today. And then you'll see in the late Holocene, blue dots will sort of take over the whole map because the whole region, most of the continent seems to have become wetter. So each frame is 1,000 years. So you can see about here, we're in the early Holocene, there's a lot of orange. But now as we get into the late Holocene, the blue takes over. And so I'll run it through again, you can see it a second time. The really key is that most places, lakes have really flooded their previous levels in the late Holocene, suggesting, except for the desert Southwest, that most of the continent has become wetter over the last 10,000 years. So of course, this is kind of the pattern that would be consistent with what we know about today. The desert Southwest is kind of the driest part of the continent, but most of the rest of the continent is quite humid. Another way of looking at this is in time series. So for a network of our sites across the mid-latitudes here, this is just sort of the average water level history over the last 12,000 years. And you see that long-term increase in effective moisture. Here's the temperatures from pollen for comparison. So that dry period in the early Holocene also is kind of the warmest period. And as things cooled off, it also became wetter. But here's where I got interested in trying to go beyond those long trends to see what were the multi-century or millennial scale features. And what we found was that if you detrend both that temperature reconstruction and the moisture reconstruction, you actually find very significantly correlated millennial scale features in both data sets. These are totally independent. This is all based on sedimentology, and this one's based on fossil pollen, but they both record a really stark anomaly in the mid-Holocene and a pretty dramatic shift about 2,000 years ago to some slightly different state. And I'll just kind of wrap up by highlighting some information about this particular anomaly here in the mid-Holocene. It's really interesting to me because if you dig into the temperature data a little bit more, what we found was that temperatures in the south actually went up during that time period. The temperatures in the north went down, and this suggests a steepening of the north-south temperature gradient. So if you plot temperatures by latitude from 45 north down to 40 degrees north here, each of these lines is a different portion of the Holocene. Most of them, the latitudinal cooling is about a couple degrees over this time, over this latitude range. But during this time period here, centered about 5,000 years ago, the gradient is much steeper. And that's important because that might be a hint that we're dealing with something like the North Atlantic Oscillation, which is an important form of variability within the climate system today, by which the Atlantic, the pressure field of the atmosphere over the Atlantic fluctuates in terms of how intense the differences between north and south. And it oscillates on monthly to annual to decadal timescales, and possibly out to these millennial timescales. But one of the things it does is it shifts that north-south gradient. So it will warm the northern part of North America, but cool the south in one phase, but in the other phase, it'll warm the south while cooling the north. And so in its sort of positive phase, it creates this very steep north-south gradient, which is what we seem to be seeing in mid-Holocene. What's interesting about that is when the North Atlantic Oscillation does that, it actually also alters the delivery of moisture to eastern North America. So you can get regions that receive more precipitation and other regions that receive less. And in fact, that's what we see in our lake level reconstructions. If we go from the coast of Massachusetts here inland to north central Pennsylvania, this is a set of reconstructions. Each blue line is a different lake over the last 7,000 years. And shaded here in orange is that time period. What you see is the coastal sites here get wetter during that time period, while the inlet sites all seem to have a low water level and a really pronounced evidence of drought at that same time. And it may be consistent with this sort of shifting of storm tracks like we see during certain phases of the North Atlantic Oscillation. And I'll just wrap up by showing you that this is not a trivial change in the water supply. It's actually, I'm kind of shocked at how significant this change was. This is Sunfish Lake, the westernmost lake in that previous slide in central Pennsylvania. This is the work of Tessa Ray Cousins, who's a current master's student. Here's a ground penetrating radar image of the shoreline of that lake. So here's water, here's the modern lake bottom. This is the bedrock and sill underneath. And then this is all mud that's accumulated. And the uppermost layers of that mud extend all the way up towards the modern shoreline. But there's a bright reflector in here that does not extend all the way up to shore. And it appears to represent a unit that is truncated out further offshore from where it is today, suggesting a time period where the lake is low. And so what Tessa did was work with the sediment core collected through that feature, plus one out in the middle of the lake. And this is some of the stratigraphic data. Here's a picture of the lake. So you see it's like in this high elevation, relatively high elevation in the Appalachian Mountains. This little pond, really wet. You can see it, the picture is taken on a rainy day, totally wet place. In the core collected near shore, really there's been very little sediment accumulation except for in the last 2,000 years. So if you look at the black line here is the organic content of the core. The orange is the sand content. For most of the last 14,000 years or so, 16,000 years, that was a sandy nearshore environment. And then about 2,000 years ago, the water level rose enough to submerge those sands deeply so that organic rich muds accumulated. The two exceptions to that were during the Younger Dryas and the Heinrich Event 1, which are two cold periods in the North Atlantic region that seem to have also raised the water level at this site. But otherwise, the lake was quite low, and this site, which is in 2 meters of water today, was actually the shoreline. But what's amazing to me is if we go to the middle of this lake, go out to in almost 6 meters of water and take another core, we also find that sand extends all the way out to that core and creates a short little unconformity in that sediment sequence from about 5,500 to 4,500 years ago. And so this is 8 meters below the modern water level. And in order to move sand all the way out to that portion of the basin and actually create an unconformity in that core sequence would require a pretty dramatic change in the water supply. And it's just interesting to me to realize that this is not some long Holocene trend. It's just a really short event, which we see recorded at multiple sites, but really affecting, a high elevation lake in the Appalachians pretty dramatically. So I'll stop there and just point out, hopefully what you've taken away from this is that our water supply has not been stable over the Holocene. Our hydroclimate has undergone some pretty significant changes, and that the low snowpack for most of the Holocene and the Rockies really raises the possibility that there are threats to that water supply today as our climate changes. But that there's also a very broad spectrum of variability from long trends to interannual droughts, but also even sort of century or millennial scale droughts, and that those can affect even very humid places like in the East, and that we should think about them as part of the natural spectrum of internal variability in our hydroclimate. All right, well, thanks so much. I appreciate you listening. Happy to take any questions.
Okay, we've got time for questions.
Yeah, Andy.
So, the basal radiocarbon, could you go back to that slide?
Sure, yeah.
That's really interesting. But I was wondering when you were showing that and your interpretation, whether you considered an alternative possibility to explain this data. And that would be, are there completely filled in places that are no longer depression
Right.
that would have that? In other words, is this something about the dynamics of how holes get made
Right.
in this area that they only last for 6,000 years?
Yeah, I mean, the interesting thing about this landscape is that the soils are incredibly thin. And so there are almost no depressions other than the ones that fill with water. And there are some depressions that today seasonally will fill up with water, but they drain so quickly they don't accumulate sediment. They're only full for a few weeks instead of most of the summer. But we have not, despite our best efforts to kind of probe around, and we actually did a big aerial electromagnetic survey, geophysics survey of this whole region. And using that, we did not detect any places where there's just stored sediment on the landscape. But I agree, that's a really great question, because you're right. Like if this was a dynamic landscape, you might fill up one place even while another basin would
It's just an equilibrium kind of.
exactly. Yeah. No, I mean, I don't know that this means there never was sediment or water in these basins before, but what's interesting is that there's none of these basins have any hint of older sediment. These are the oldest dates, the oldest sediments we could get out of those basins, suggesting they really did fill up in the late Holocene.
If I could ask another question, completely unrelated. 8,200 year event.
Yeah.
Do you see this? And is there any particular pattern to it across North America?
There is. So it's actually a really significant feature. The 8,200 year event is where the final main dome of the Laurentide ice sheet collapsed, and that fundamentally changed the way the atmosphere circulated over North America. And what we see is in the mid-continent, like at our lake level sites in the Rockies, but also definitely across the northern Great Plains, a lot of regions dry out really precipitously at that time. Whereas on the East Coast, many lakes rise really sharply. And we see less of the event, like the 150-year 8.2 event, and more of just this step change from us. Basically, and the way I think about that is we're going from a climate state where the ice sheet is really influential to one where it's not there. And it's basically a step change. And because you had a big high pressure system sitting over that ice sheet, the loss of that high pressure system meant more moisture could get evected into the East Coast while actually being prohibited from getting into the mid-continent. So we see this kind of east-west shift in the water supply.
Questions? Student questions are encouraged. There we go.
Given, if I understand it correctly, your snow study here is mostly limited to northern Colorado and southern Wyoming. Geographically, how should I interpret whether this scales up or not?
Yeah.
Given that the mountain west is quite complex climate in terms of climate and its ability to get snow.
Yeah, that's a great, let me just jump ahead back to this slide here. Oops, not that one. That's the right, that was the right one. But the, yeah, so this pattern here of evidence of there was less snow in the early Holocene and more snow in late Holocene, certainly it does not have to be uniform across the Rockies. And I would expect that maybe there's really different regions. What has surprised me about this is that this is northern Colorado, but up in northern Wyoming and the Tetons, there was a recent study that looked at the history of the Teton Glacier using a very similar technique, actually, and found virtually the same history. And then there's actually further north, right on the Montana border, there's a snowfield where a group cored the snowfield and actually found layers of debris in the ice field and radiocarbon dated it. And what they found was the accumulation of ice in the snowfield itself followed the same pattern. And so at least basically across the state of Wyoming, from southern Montana to northern Colorado, there seems to be a lot of agreement. Whether that extends beyond that, I don't know, but at least for this region, there does seem to be emerging coherence in the data. And I mean, hopefully we would get to do more of this work in other places to really map that out. But it's a good question.
We have a question from the chat here. Thanks for the talk, Brian. Do you see changes in fire frequency along with these broad precipitation trends?
Yeah, great question. So we've done a lot of work looking at some of these same lakes and counting layers of charcoal in the sediment to look at the frequency of wildfire through time. We've done this both in the east and in the west. In the Rockies, we actually don't find a really strong coherence. We mostly have just worked on the late Holocene, so this kind of wetter time period. It would actually be really great to go deeper in time. But on the short time scale of the last 2,000 years or so, we don't see much evidence of a really tight coupling with moisture. You know, if anything, we see a better coupling with temperature. And in fact, most of the sites, if you take kind of northern Colorado, most sites burned, or most centuries had about 30% of our study sites showing evidence of fire each century over the last 2,000 years. But about 1,000 years ago, during the medieval period, when it was maybe slightly warmer, we saw evidence that actually 110% of our sites burned because several of them maybe burned more than once during that time period. And so it does seem as though there are some significant fluctuations in fire history, but they potentially seem more directly controlled by temperature, which is what we're seeing now. In the east, it's actually a really interesting pattern. The east, of course, is also getting wetter through time. If you look at the layers of charcoal in the sediment cores there, what we find is that there was an early Holocene peak in burning, and it seems to be a trade-off between it being really dry early on, but also a shift in the fuel type. So the more oak trees you have in the landscape, the more likely you have the fuels to favor fire. And so we get kind of a peak there when it's still quite dry, but you have a lot of oak trees around that can burn. And so there's actually a really interesting interaction between fuel availability and the climate. And it wasn't simply, the pattern does not seem to be simply explained by one or the other. So yeah, I think I mean, we're experiencing such a dramatic change in wildfire behavior now. These data pretty clearly show that we're moving outside of that history, that range of variability that we've experienced in the past, but they definitely highlight the fact that climate can have a really dramatic impact on fire.
Yeah, question. The sort of the millennial scale to centennial scale changes you see that are remarkably coherent in some of the reconstructions. What do you think is driving those?
Yeah, so this one pattern that I was sort of talking about there seems like it could be tied into shifts in the pressure field over the North Atlantic, like North Atlantic oscillation type behavior. And that could be just totally intrinsic variability in the climate system, right? Like it doesn't have to be, there doesn't necessarily have to be some external forcing on that. That could just be the frequency at which that process varies on those timescales. But superimposed on that, there's actually another pattern of coastal versus inland variability, that where the coast gets wet when the inland areas get dry, and vice versa, that has a very different temperature set of changes associated with it. And what's interesting about that is that today, if you look at the same areas and look at what makes the coast wet when the inland areas are dry, the primary explanation for that is El Nino. Even though we're talking about like New England, the El Nino has an influence on the Atlantic storm track that brings moisture up the East Coast. And so during El Nino winters, the coast gets just a lot more snow than inland areas. And so there's actually a pretty stark change in that coastal versus inland area contrast. So again, that doesn't necessarily mean that's what explains the pattern in the Holocene, but it raises the possibility that, again, intrinsic variability within the climate system, maybe in this case coming from the Pacific, could also be influencing what we're seeing here. I think there's a lot more work to really tease that apart, and I'd be interested to dig into that. But you know, and it's certainly possible that things like volcanoes and maybe even solar variability are sort of modulating the timing of some of that millennial variability. But it does seem to be real, and it's worth trying to dig into to understand what the mechanisms are.
Any other questions?
Yeah, I have more of a comment on that actually. So I have a student that is looking at the last interglacial period,
Yeah.
which is kind of the end of that, let's say 100,000 years before this time period. And we're looking at that time period through a long transient simulation with the climate model. And we actually see a similar thing. We have something that kind of looks like a permanent negative phase of the MAO that then transitions to the positive phase
Interesting.
through the last
Over the course of the interglacial.
yeah, so over 10,000 years.
Yeah.
I don't think it's actually NIO necessarily. I think it's some sort of internal variability that has the signature of NIO.
That's the way I've been thinking about this too. I mean, I don't think I should really characterize this as MAO. It's just that mode of interannual variability is a good maybe analogy for how to think about this dynamic on these longer time scales. Yeah, I mean, that's interesting. I mean, I can imagine, I mean, we know for sure that, you know, orbital changes influence the intensity of that pressure field. So we should almost expect there to be this full spectrum of variation from the monthly scale all the way out to those orbital scales with millennial possibilities in between. So that's, but that time scale, I still think is the least well-defined portion of the climate spectrum. We really just don't know what that looks like. And what are the major modes of variability at century millennial timescales? And that's something I think is really worth us trying to resolve as a community.
Any other questions for Bryan? Okay, we have a round of applause. Thank you, Bryan. You could just move your tables and make one of them meet with each other like we do every week.
Sorry.